Welcome to the debate. Right now, inside your own body, thousands of potassium-40 atoms are violently ripping themselves apart every single second.
Yeah, it's honestly a bit terrifying when you think about it.
It really is. I mean, it is a continuous, microscopic detonation of matter. We just walk around with this terrifying physical reality every single day.
Right, entirely, completely oblivious to it.
Exactly. Yet, if you were to write this exact process out on a chalkboard, it would look like a completely harmless, perfectly balanced algebra equation. It just looks quiet.
Almost too quiet, honestly.
Yeah, and that stark contrast brings us to a really fascinating pedagogical crossroads today. It's one that was captured in a recently recorded educational session we were reviewing.
Right, where an instructor was guiding students through the mechanics of radioactivity.
Specifically, focusing on details for students like Matilde and Tala, who were trying to wrap their heads around this stuff for the first time. So the debate we are having today centers on a fundamental question of how we teach science.
Right, like when introducing the complexities of nuclear physics to beginners, what should the primary focus actually be?
And my position is quite clear. The fundamental pedagogical focus for students must be the immutable mathematical frameworks, specifically, the law of conservation of mass and atomic numbers, because mastering this logical system is really the universal key that unlocks any nuclear equation.
And, well, my position is that the primary focus must be on the physical realities of the particles and the vast scales of radioactive decay. Because, honestly, treating radioactivity merely as mathematical bookkeeping, it obscures the violent, dynamic, physical nature of the universe.
I get why you'd say that, but to see why the mathematical framework is the supreme pedagogical tool, we really just need to look at the foundational rule of radioactivity taught to these students.
The conservation laws?
Yes, exactly. The law of conservation. In any spontaneous transformation, the sum of the mass numbers, the A values, and the sum of the atomic numbers, the Z values, before the arrow must exactly equal the sum of those numbers after the arrow.
A sterile accounting ledger, basically.
See, some might look at it and see an accounting ledger. I see an expression of fundamental universal symmetry. I mean, think about the profound predictive power this gives a student like Matilda.
Predictive power, sure. But does she understand what it means?
Well, an element's atomic number acts as its definitive ID card, right? If Z is 92, it's uranium. If Z changes, the identity changes. By understanding the simple structural relationship that the number of neutrons is the mass number minus the atomic number, a student can logically deduce the outcome of any radioactive event.
Right, they just do some basic subtraction.
Exactly. And because of that, they don't have to memorize a massive catalog of reactions. They can sit down with a completely novel problem and just, solve it independently. This mathematical scaffolding builds genuine scientific confidence.
I mean, I guess it gives them the right answer on a test.
It does more than that. It protects students from throwing up their hands and relying on superficial shortcuts. Or, using AI tools like ChatGPT to do the thinking for them, which we know is a huge problem right now.
Well, I come at it from a different way. I completely agree that independent problem solving is the goal, right? And bypassing the cognitive struggle with chatbots definitely ruins the learning process.
Totally ruins it.
But we have to ask what we are actually teaching them to solve here. The essence of radioactivity is physical, not algebraic. The numbers on the page are just shadows of the actual event.
Shadows? That's a bit poetic, don't you think?
No, it's true. Knowing that an alpha particle is mathematically represented by a mass number of 4 and an atomic number of 2 is frankly a hollow vessel of information compared to understanding its actual physical reality.
I see why you think that. But let me give you a different perspective. If the physical reality of the nucleus is so phenomenally complex, and it is, isn't the simplest mathematical model the absolute best safe harbor for a student's initial understanding?
A safe harbor shouldn't be a blinding one, though.
Well, let's take a specific pedagogical example from the material. Consider the decay of bismuth-212. A student doesn't need to be overwhelmed by quantum mechanics to figure this out.
Okay, but bismuth is a great example of where the math falls short.
Let me finish the thought. Bismuth has a Z of 83. The conservation law dictates exactly what happens next. If it undergoes alpha decay, the math tells the student to subtract 4 from the mass and 2 from the atomic number.
Right, which takes them to 81.
Yes, they get 81, they check the periodic table, and they know immediately it's thallium. It is an infallible, logical deduction. If it undergoes beta minus decay, the arithmetic dictates the atomic number actually increases by 1, bringing us to polonium.
So it's just moving numbers around columns?
Once a student masters this ledger, the physical complexities don't matter as much. They possess a structural truth that holds firm no matter what element they are looking at.
I'm sorry, but I just don't buy that. Let me tell you why. That exact bismuth example highlights the profound danger of over-relying on the math. It flattens reality into an illusion of sameness.
How is it an illusion? The transformation actually happens.
Sure, but when a student balances that beta minus equation, they are writing down a mass number of 0 and a z of -1. It looks like a minor tweak to the ledger, but physically,
It's an electron emission.
a beta particle is an electron being ejected at incredibly high speeds, often upwards of 270,000 kilometers per second. Now compare that to the alpha particle, which is a bulky helium nucleus.
Bulky is relative, but yes.
Because the alpha particle has a mass of 4 and a +2 charge, it interacts electromagnetically with practically every atom it passes. It rips electrons off neighboring atoms, dumping its kinetic energy almost instantly.
Which is why a piece of paper stops it.
Exactly. That's why a mere sheet of paper stops it. The beta particle, being minuscule and incredibly fast, punches right through that paper and requires a sheet of aluminum to stop it.
Okay, but hold on. My point is, by teaching the student just to add or subtract 1 from the z column, you are completely stripping away the mechanism of how these particles interact with the physical world.
But the mechanism of interaction isn't the focus of a decay equation. The decay equation is simply about the transformation of the parent nucleus.
But the omissions get worse. Look at gamma radiation. Gamma is mathematically represented as having a mass number of 0 and an atomic number of 0. Yes, 0 over 0.
On a ledger, 0 over 0 literally adds nothing and subtracts nothing. A student looking purely at the math might logically deduce that gamma is completely irrelevant.
Well, they shouldn't, because it's accompanied by energy.
But gamma isn't even a particle in the traditional sense, right? It's a high-frequency electromagnetic wave. It has no mass and no charge, meaning it ghosts right past the electron clouds of other atoms.
It's highly penetrating, yes.
It takes thick blocks of dense lead to finally interrupt its path. If you just balance the numbers, you are failing to teach the student that this mathematically invisible emission is actually the most lethal and penetrating radiation of all. You're teaching algebra, not physics.
Okay, I'll admit, the 0 over 0 reality of gamma radiation is a genuine blind spot if a student is only looking for structural changes. It is easy to see a 0 and just dismiss it.
Thank you. It completely erases the physical threat.
But let me push back on how we frame that. The zeros don't mean gamma is physically irrelevant. They accurately reflect that the structural identity of the nucleus has not changed.
Which is mathematically true, but physically misleading.
The Z number, the ID card we talked about, remains intact. The math is doing exactly what it is designed to do, which is track the conservation of nucleons. Which naturally shifts our focus to the nucleus itself and the concept of isotopes.
Oh, right, isotopes.
The material places a really heavy emphasis on making sure students like Tala and Matilde grasp this specific concept.
And it is a notoriously tricky concept for beginners. They always get tripped up on it.
It is, unless you rely on the mathematical definition, which is taught with exquisite clarity in this session. Isotopes are defined as atoms that possess the exact same atomic number Z, but a different mass number A.
Sure, structurally speaking.
Because the foundational formula is A equals Z plus N. It logically dictates that if Z is constant and A is fluctuating, only the number of neutrons, N, can possibly be changing.
It's a neat algebraic trick.
And it is a perfectly self-contained logical deduction. The student does not need to visualize the invisible swirling interior of a nucleus. They just need to know that the protons define the element's identity, so the varying mass has to be the neutrons. It is clean, precise, and highly functional.
That's a compelling argument,
But have you considered that focusing purely on those Z and A variables completely ignores the fundamental mechanism of the phenomenon?
Student, equations on a chalkboard aren't unstable. Physical objects are.
The numbers represent the instability.
If a student just memorizes the formula for neutrons, they miss the underlying drama happening inside the atom. Think of the nucleus like a tightly packed, spring-loaded box.
Okay, I'm with you. A box.
Inside that box, you have two fundamental forces at war. You have the strong nuclear force, which acts like an incredibly powerful glue, but it only works at incredibly short distances.
Right, between adjacent nucleons.
Exactly. And you have the electromagnetic force, which is the repulsion in between all those positively charged protons trying to push each other apart. And that force operates over a much longer range.
Which is why the neutrons are there, to act as a buffer.
Exactly. The neutrons add more of that short-range strong force glue without adding any more electromagnetic repulsion. But as the nucleus gets larger and larger, or if the ratio of neutrons to protons gets too skewed,
The box breaks.
that spring-loaded box can't contain the tension anymore. The short-range glue can't hold the outer edges against the relentless outwards push of the protons.
So it decays.
The physical instability, the absolute mechanical necessity of the nucleus to violently eject a piece of itself to find a stable configuration is the core engine of radioactivity. If you just tell Matilde that an isotope is a change in the variable n, she is completely missing the intense physical tension that causes a decay to happen.
I'm not convinced by that line of reasoning, honestly, because understanding the physical tension of the strong nuclear force doesn't actually help a student calculate the outcome of the decay on the exam in front of them.
It's not just about passing an exam, though.
The pedagogical goal here isn't just to foster awe, it is to build a functional capability. When Matilde looks at a radioactive isotope, she needs to recognize its structural components and calculate its decay path.
But she's calculating a path blindly.
Visualizing a spring-loaded box is a great metaphor, I'll give you that. But it doesn't tell her whether the atomic number is going to drop by 2 or increase by 1. The mathematical framework provides the operational rules.
I understand the need for operational rules, but mastering the A and Z numbers of a single decay event tells the student absolutely nothing about when that event will happen.
Time is a different variable, obviously.
If you just look at the algebraic deduction, a fraction of a second looks identical to a billion years. The math alone gives no sense of time, which brings us to how students are taught the concept of half-life.
I actually welcome that pivot because half-life might be the most elegant mathematical progression in the entire physics curriculum.
Elegant. It's completely devoid of context.
Let me explain. The definition given to the students is highly precise. Half-life, denoted as T1/2, is the duration required for exactly half of the initial quantity of a radioactive sample to decay.
Yes, that's the definition.
If you start with an initial mass, m0, the half-life is the time it takes to reach m0 divided by 2.
You're just describing the curve on a graph.
I'm describing a universal, predictable progression. After 1 half-life, it's divided by 2. After 2, it's divided by 4, then 8, and so on.
But you're just slicing up a hypothetical pie.
Whether you are counting the initial mass or the initial number of undecayed nuclei, the mathematical operation is beautifully symmetrical. It gives a student a highly reliable framework for conceptualizing time in nuclear decay. They just follow the exponential curve.
But the curve is deceptive because it flattens the extreme mind-bending variances in the physical data. Yes, dividing by 2 is the mechanical operation, but look at the actual timescales the students are presented with.
The timescale doesn't change the curve's shape.
The material notes that an element like astatine has a half-life of 3.2 times 10 to the negative 2 seconds. That is 3/100ths of a second. Half your sample physically vanishes in the literal blink of an eye.
Right, very fast decay.
Then you have nitrogen at 7.4 seconds, iodine at 8.1 days.
The proportional rate of decay is identical in all those examples, though.
Proportional, yes, but then the material presents carbon with a half-life of 5,700 years, and uranium, which stretches to a massive
7.2 times 10 to the 8th power, nearly a billion years.
Which the formula handles perfectly well.
If you teach students to just view this as plugging different numbers into the t variable of an equation, you fail to impart the staggering scale of the cosmos. The mechanism might be the same, but the reality is not.
I think they understand that a billion is bigger than 0.03.
But do they feel the weight of it? One element flashes out of existence while you're taking a breath, and another persists longer than continents have existed on Earth. The physical timeline determines whether a radioactive material is a fleeting laboratory curiosity or a permanent geological hazard that will outlast human civilization. You just can't capture that with m0/2.
I hear your point about the vastness of the scales, and it is humbling. It is. But pedagogically, a student cannot reliably calculate the remaining mass of a uranium sample after a billion years by merely feeling awestruck by deep time.
They should understand the context.
They need the formula. They need to know that the mass at any given moment is a strict mathematical function of that initial quantity and the number of half-lives that have elapsed. We are trying to build scientists here, not just philosophers.
Physics is the philosophy of nature, though.
Providing students with robust mathematical frameworks, the immutable rules of conservation, the structural logic of A and Z calculations, and the rigorous half-life formulas gives them independent agency. It allows them to systematically deconstruct complex scientific phenomena.
As long as they don't get lost in the abstraction.
When a student like Tala internalizes that math, she doesn't need to memorize a textbook, and she certainly doesn't need to offload her thinking to an AI chatbot. The math is the foundational scaffolding of all physical understanding.
And my conclusion remains that a scaffold without a building is just a collection of metal poles. The math is incredibly useful, I'll admit that, but it is ultimately subservient to the physical universe.
I wouldn't say subservient, maybe parallel.
Without anchoring those neat algebraic equations in the messy, extreme realities of physics, understanding that alpha gets snagged by paper while gamma requires thick lead, visualizing the delicate war between the strong and electromagnetic forces inside the nucleus.
The spring-loaded box?
Exactly. And confronting timescales that stretch from milliseconds to hundreds of millions of years. Without all that, the math remains a hollow exercise. It becomes merely a practice in shuffling numbers across an equal sign. The universe isn't just balancing an accounting ledger. It is acting out a fierce and dynamic physical reality.
I think where we fundamentally converge, however, is on the absolute necessity of direct, step-by-step engagement with the material itself.
Oh, 100%.
Whether a student is grappling with the rigid, unforgiving logic of the conservation laws or trying to wrap their mind around the extreme physical scales of half-lives, the true learning happens in the cognitive struggle.
Absolutely. In fact, the instructor's specific praise for Mathilde's persistence really highlights this core truth. There are no shortcuts to understanding the universe.
None at all.
Taking the easy way out, whether that is rote memorization without comprehension or using a chatbot to instantly spit out an answer, it circumvents the very process of learning. You have to wrestle with it, whether you are trying to balance the Z numbers or trying to conceptualize a wave traveling at the speed of light.
There is clearly much more to explore in how we translate these incredibly complex, universal phenomena into digestible lessons for students.
There always is. It's a never-ending challenge.
It leaves us to reflect on whether the true beauty of science lies more in its immaculate mathematical symmetry or in its violent, awe-inspiring physical extremes. We started today talking about decay equations written neatly on a chalkboard.
Right.
It makes you wonder, when a student finally balances that final equation, checks their work, and puts the chalk down, do they see a closed system of numbers, or do they see a star burning itself out in the palm of their hand?